So area between two curves. We kind of talked about this for a second during Unit 6, I think. But we're going to go far more in depth with finding areas and then ultimately finding volumes. Okay? So let's see what we got here. So let's say we have a function that looks like this, and I want to find the area between it and the x-axis. It, the function, and the x-axis. What would I have to do? Let's say this is A, this is B. What's the area between the curve and the x-axis? The integral from A to B of whatever that function is, right? Okay, so assuming I want it to stop here to there, right? Now what we're going to do is we're going to add something like this. And I'm going to ask for the area of this region.
Can you subtract the integral of AB of whatever that
So we're going to say, we'll call the black curve f of x, and then the red curve we'll call g of x. So what would the equation be?
minus integral of AB of G of X.
So this integral gives us this whole area, right? Minus what integral?
A to B of G of X.
The integral from of a to b of g of x dx, that gives you this region below, right? And so when I subtract them, I'm left with the region above. Does that make sense? Okay. Now I can simplify this equation. How? The integral from a to b of f of x minus g of x dx. This is wrong notation. You got to have brackets or parentheses around all of that to say the dx goes with all of it. You guys okay with that? So let's take a look at an example here. Same thing. Now what? If I want the area of the region that is between those two curves, what region am I talking about? That's a good description right there. Where does it start? Right. The region that we're looking for is bounded by the purple curve and the blue curve, which means the integral is going to start at their intersection and end at their next intersection, right? Okay. Here I gave you kind of artificial bounds, so we would say that it's the area bounded by the two curves and the vertical lines x equals a and x equals b. But here it's bounded by the two curves because they intersect. Okay. So we're looking for the area of that green piece. Can you see it? Yeah. So now what would you say the equation is there? Why g of x minus f of x in that case? Right. Which one's the lower function? F of x is the lower function within the region that we're talking about. Now f of x is higher in other places, but because we're only talking about that particular region, we're going to say g goes on top, or g first. So what's the area of g? Just to integral from a to b of g of x. So it looks like this, though. When I say find the integral of g, or the area of g, we're finding that region. You guys okay with that? So that's the integral from a to b of g of x. The area of the area of f, where am I getting that from? Area of f is this region. Kind of hard colors to see. You see how it's the below region? Okay. So that's the integral from a to b of f of x dx. And then to find out the area of that green region that I had originally, I'm going to take those two and subtract them. Of course, you always want the bigger area to go first. Why? If you're finding negative area, you're finding like a net area, which might be applicable to some context in calculus, but when we're talking about area, it's going to be positive. Okay? So the area of the purple minus the area of the blue, therefore it's going to be the integral from a to b of g minus the integral from a to b of f. And again, that simplifies. I'm still seeing some people do this, by the way.
Why did you put area of blue? Why did you put area of F?
I don't know.
I
That should say area of G minus area of F, right? Sorry. I'm still seeing some of you apply this imaginary rule here.
Crap, that's why I got the text. That's wrong.
This is what I'm seeing some of you do. The integral of a product is the product of the integrals? No? Or even division? No. The only way this works is if this is plus or minus, right? You got to do something else. It might be use substitution, it might be integration by parts, which you haven't learned yet. It might be a bunch of stuff. All right, can I go on? You didn't get what?
On the bottommost corner, is that? Okay.
That's putting it together into one equation. All right. All right, going on. Didn't I already ask this question? All right, so I guess the steps that you need to look for are determining which function is greater. In this case, G is greater in this region. Determine where the curves intersect, right? And they intersect in this case at A and B, whatever they are. Do you guys know how to find the intersection points on your calculator? You have Y1, you have Y2, you graph it, what do? You press intersection. It's in the same list as the zeros. You press intersection, and then it'll say first curve. You put your cursor on one of the curves, hit enter. Second curve, put your cursor on the other curve, hit enter. And then it'll ask for lower bound, so you move to the left of the intersection, hit enter. Upper bound, move to the right of the intersection, press enter. How would you do it analytically to find the intersection? Set them equal to each other. Okay? And then from there, you set up the integral, making sure that the greater function goes first. So if G is greater, then it's going to be G minus F. Okay? So that's kind of just repeating what we said. We okay with that? Seems kind of easy, right? If I'm looking at the blue curve, yes, the blue curve is above the purple curve in here, but I don't care about that. I care about in here. The purple curve is bigger, so G is bigger. Okay. So let's look at an example. What is the area bounded by that? What's that going to look like? You got a parabola. What's negative 2x to the fourth look like? Say that one more time. X to the fourth has 3 bumps, and this one opens down. So it's going to go like this, but because there's no extra parts of that equation, it's actually going to look very similar to a parabola. Okay? So if I'm going to graph this, you got x squared. You guys okay with that? Okay. Negative 2x to the fourth looks like this. Okay. Notice how it's just kind of wider at the x-axis, or at the origin. What did you say? Well, just observing that negative 2x to the fourth is always negative, right? Because x to the fourth is always 0 or positive, right? And as x gets bigger, as x moves away from 0, you're going to keep getting bigger and bigger values. Either side, you're just going to keep getting bigger and bigger values. Yeah, you need to look at the graph to understand this. Now notice it says bounded by x equals negative 1 and x equals negative 1 and 1. So what am I looking for here? What region? Can you visualize the region that I'm trying to find? Yeah, kind of sideways triangles, right? So when I say x equals negative 1, that's there, and x equals 1 is there, right? And we're looking for the region bounded by all of that. So we're looking for this area up here? No, we're looking for this region and this region. Okay? So we're looking for those pieces. Now remember, in this case you don't have to find intersection because those functions don't necessarily intersect. You do have to be careful though. Where's there a point where something might change? at the origin because right here, maybe the purple curve moves right slightly above the blue curve. Does that happen in this case? No. So what is the upper curve in all of this? Y equals x squared. What is the lower curve? Y equals negative 2x to the fourth. So what's the equation here? To find the area of those green regions. The integral from negative 1 to 1 minus. Okay. Now some of you might be looking at that going, wait a minute. Negative 2x to the fourth is below the x-axis, right? So let's explore that just for a minute and see what we come up with. What is the integral of x squared from negative 1 to 1 going to produce for me? What kind of value? It'll be a positive value, right? And the integral from negative 1 to 1 of negative 2x to the fourth dx will give you what? A negative value. Remember, what are we supposed to do with those functions? We're supposed to subtract them. But does subtracting make sense? Well, if I say a positive minus a negative, what am I doing? I'm adding the areas, right? So this area kind of becomes positive, so we're finding the area here. We want the positive value of that area, and we're adding it to the positive value of that area. So you don't have to worry about the signs. It's just always the upper curve minus the lower curve, no matter where the curves are. All right. So the integral, let me simplify it for you. Integral from negative 1 to 1 of x squared plus 2x to the fourth, right? And I'm still seeing some people and hearing some people do this. 1 squared plus 2 times 1 to the fourth minus negative 1 squared plus 2 times negative 1 to the fourth. Why? They didn't take the antiderivative. So what's the antiderivative? 1/3 x cubed. And then evaluated from negative 1 to 1. So we got, I'm just going to do the ones here. You got 1/3 plus 2/5. You guys okay with that? Minus negative 1/3, because that will be negative 1, minus 2/5. And yeah, it kind of looks like it might cancel out, but it won't, because you got Adam. So this is 1/3. Let me get common denominators here. What do we got? 5, so what? 5/15 plus 6/15 plus 5/15 plus 6/15. So that's 22/15. Now notice, what would be another approach that you could have done in this particular case? How? Okay, you could have done the integral from negative 1 to 1 of x squared, and then minus the integral from negative 1 to 1 of negative 2x squared. You could, or 2x to the fourth. You could have done that. But what did you say? Right. And what do we notice from negative 1 to 0 and from 0 to 1? They're the same. It's a symmetrical. These are both, what are they called? It's symmetric across the y-axis. What's that called? Even functions. Even functions, right? Now, you could do it that way in this case because these are even functions, but not necessarily always, okay? All right. And that simplifies to 22 or 15. Are we good with this? Any questions? All right. Going on.
One more unit to go.
All right, you guys think through this without a calculator. You should have gotten that.
No, Mr. Bernier, I did the window.
All right, let's go step by step here. Okay. Sine looks like this, right? And we're looking from the y-axis to pi over 4. So where's pi over 4? Pi over 4 is there, right? Isn't it?
No, that's pi over 2.
Where's pi over 4? Okay, pi over 4 is there. Okay, but still. Now, if I'm looking at the secant function, I've got to look at cosine first. Cosine looks like this, right? That's something like that. Yeah, that's right. Okay. That's cosine, right? Secant squared, notice it's squared, so the value is always going to be positive. Remember, secant looked like this. It bounced off the top of cosine. Okay? Now, secant squared just means that this is going to accumulate a lot faster. So we're looking for the region that's bounded from here at x equals pi over 4. So we're looking for just this piece right there.
Can you like put that on the screen?
Yeah, see, if it's not going to be anything. Maybe change your window. So change your window from 0 to pi over 4 and from the y value 0 to what is this point of secant. What's secant of pi over 4? Rad 2 over 2, so 2 over rad 2. 4 over 2 is 2. Change it to, so your y max is 2. You guys okay with this? See it? So now we're looking for the region that's bounded by the y-axis and pi over 4. So we're looking for that piece. Analytically, what's the equation now? Come on, guys. The integral from 0 to pi over 4 of secant squared x minus sine of x and dx. It's easy stuff. What's wrong? What is the antiderivative of secant squared? So tangent of x, and then this would be plus cosine. What are we going to do every time? Take the derivative, see if it matches. What's the derivative of tangent x? What's the derivative of cosine? Negative sine, right? And then this is evaluated from 0 to pi over 4. So what's tangent of pi over 4? Minus tangent of 0 plus cosine of 0 here. What's tangent of pi over 4? 1. What's cosine of pi over 4? So plus rad 2 over 2. Minus, what's tangent of 0?
0.
What's cosine of 0? So we've got the 1 minus 1, so you're just left with rad 2 over 2.
Wait, no, but since you subtracted
Again, if you want, you can separate it. Find the area below secant squared, find the area below sine, and then subtract. It's just maybe adding a little bit more steps than you would want. All right, any questions with this? Doesn't seem too difficult, right? All right. No excuses on this one. If you can't do this without your calculator, go back to Algebra 1. I'm dead serious. All right, graphing. You should have gotten a graph with a negative parabola and a y-intercept of 2, and then a negative linear with a slope of negative 1 and y-intercept of 0. So when I say find the area has to be enclosed. I can't say find the area of this thing. Right? It has to be enclosed. So if I enclose it, is that region, the reason I pointed that out, is that region, that's this region over here, in order to enclose it, I need more information. I didn't give you more information. So what is the region that's enclosed by these two pieces, or these two functions? It's the bounded part. It's the area below the parabola and above the line. Okay? So are we good with that, understanding that? What do I have to do first? Find the intersections. We find the intersections by setting them equal to each other. So points of intersection would be 2 minus x squared equals negative x, and then you're going to solve for 0 and then factor. So your intersections were negative 1 and 2. So now what's your equation? Integral? From negative 1 to 2 of 2 minus x squared minus negative x, so it's going to turn into plus x. And then we take our antiderivative. You got 2x minus 1/3 x cubed plus 1/2 x squared. And then we're going to plug in our upper and lower bounds. We end up with something that is 9/2, yeah?